Hey everybody, my name is Kelvin and welcome back to my channel. Today we're going to be talking about PCA, which stands for Principal Component Analysis. The name might sound a little intimidating at first, but the main idea here is actually really approachable once you connect it to a real problem. A lot of datasets have way more columns than we can easily understand or visualize. For example, you could have a dataset with 10 features, 50 features, or so on, and many of those columns may overlap with each other in some way. One column might not be exactly the same as another, but they may still be just capturing a similar pattern. PCA gives us a way to take that high dimensional data and then represent it using a smaller number of new features while trying to preserve as much of the important structure within the dataset as possible. The new features created by PCA are called principal components, hence principal component analysis. The first principal component will capture the strongest direction of variation in the data. The second principal component captures the next strongest direction, and then each additional component will continue that process. You can think of PCA as rotating the data into a new coordinate system where the biggest patterns here are easier to capture with less dimensions. That's why PCA is useful for visualization, preprocessing, and exploratory data analysis. If we can reduce a dataset from 13 features down to just two principal components, we can plot it on a regular 2D graph and start to see whether there are clusters, outliers, or other interesting structure in the data. In this video, we'll load a toy dataset, we'll inspect the data, scale the features, run PCA, and then we'll visualize the result. And then we'll take a look at the explained variance so we can understand how much information our reduced version actually keeps. To start, we'll begin with our imports. We start by importing pandas because it gives us a convenient way to work with data in rows and columns. When we turn our dataset into a data frame, it becomes much easier to inspect the first few rows, check column names, and generally just understand what we're working with. We also import matplotlib because we'll use it to create our PCA plots later in the video. PCA becomes much easier to understand when we can actually just see the lower dimensional version of the data. And then the last three imports will come from scikit-learn. Here, we'll use load wine to get a built-in toy dataset about wine, standard scaler to scale the features before applying PCA, and PCA to actually run principal component analysis. Now that we have our imports, let's actually load our dataset. Load wine will give us a small dataset about different types of wine. Each row here represents a wine sample, and each column contains a numeric measurement about that specific sample, such as alcohol content, color intensity, or other chemical properties. Here, the variable x here will store the feature data, which means that these are the values PCA will actually analyze. The variable y will store the label, which tells us which class of wine each row belongs to. PCA is an unsupervised learning method, so it does not use those labels when creating the components, but we'll still keep them anyway because they are helpful later when we want to color the plot by wine class. We'll also save feature names and target names so our tables and plots are easier to read. Without these names, we'd just be looking at arrays and numbers, which is not very helpful when we're trying to explain what is happening. Run this code block, and now we have our dataset. Now, let's convert our feature data into a pandas data frame, and we can do that using pd.dataframe. Specifically, this line will create a table where the columns are labeled using the original feature names from the dataset. And then calling df.head will print the first 5 rows, which is a really simple but important habit when working with data because it lets us confirm that the dataset loaded correctly and it gives us a quick sense of what the columns look like. At this point, we can see that each row is one wine sample, and each column is one measurement about that wine. Since PCA is going to work across these columns, it's useful to pause here and make sure we understand the basic structure of the dataset before moving forward. For example, in row 0, we have alcohol 14.3, malic acid 1.71, and so on and so on and so on. Let's take a look at the shape. We can do that using df.shape. What shape will tell us is how many rows and columns are in the dataset. The first number is the number of rows, which is 178 here, and the second number is the number of columns, which is 13. This means that each wine sample is described using 13 different measurements, and there's 178 specific wines. 13 features is small enough for us to understand conceptually, but it's still too many to visualize directly on just a normal 2D graph. And that's exactly the type of situation where PCA is useful, because we can reduce those 13 original features into just two principal components, and then we can plot the result. Before we run PCA though, we need to handle scaling. Scaling matters here because PCA is sensitive to the numerical range of each feature. If one feature has values between 0 and 1, while another column has values between 0 and 1000, you might find that PCA treats the larger scale column as more important, simply because its numbers are bigger. That doesn't necessarily mean the feature is more meaningful than the other. It may just be measured in a different unit. Standard scaler here will help us avoid that problem by transforming each feature so that it has a mean of 0 and a standard deviation of 1. In simpler terms, it puts the columns on a more comparable scale so PCA is not unfairly dominated by features with larger raw values. And then the next thing we're going to do is use fit transform. This method here will do two things for us. Fit part will calculate the mean and standard deviation for each feature. The transform part will use those values to scale the dataset. The scaled result is stored in a variable I've called xScaled, and this is the version of the data we will pass into PCA. The next line here is where we're going to be doing the magic. In the first line here, we create a PCA object. In the first line here, we create a PCA object and set the number of components to 2. That means we're going to be asking PCA to reduce the original 13 features down to just 2 new components. We choose 2 components here because we want to visualize the result on a 2-dimensional scatter plot. The second line here will fit PCA to the scaled data we just created and then transform the data into a new PCA coordinate system. The output here, which I've called xPCA, now has 2 columns instead of 13. These 2 columns are not original measurements from the wine dataset. They're simply new features that are created by PCA, and we can usually call them principal component 1 and principal component 2. Let's put those 2 components into a data frame so they're easier to inspect. Here, I've made a new dataset with 2 columns, which are named PC1 and PC2 for principal component 1 and principal component 2. Then, we're going to be adding target labels back into the data frame. PCA did not use these labels to create the components. We're going to only be adding them back, so when we create a scatter plot, we can color the points by wine type and see whether the reduced representation shows any separation between classes. And we'll run this cell. And we can see the head right here. Now that we have our new data frame here, let's visualize the PCA result. This plot here will show the original 13 feature dataset compressed into just 2 dimensions. The x-axis here will act as the first principal component, and the y-axis is the second principal component. The loop here will let us plot each wine class separately. For each class, we're going to be creating a smaller data frame called subset, which contains only the rows belonging to that specific class. Then, we use the scatter method to place those points on the graph. The label argument here will give each group a name in the legend, which makes the final plot easier to interpret for us. When we look at this visualization here, we're going to be looking at 2 new directions that are created from combinations of the original features. If the points separate nicely by class, that suggests the original features will contain structure that PCA was able to capture in just 2 dimensions. That said, though, PCA is not a classifier. We have to be aware that it's not trying to predict the wine type, and it's not using the labels to create the plot. PCA is only trying to preserve the strongest patterns of variation in the feature data. And sometimes those patterns line up with the class labels and sometimes they don't. Let's take a look at this plot. Once we have the plot here, the next question is how much information have those 2 components actually preserved? We can answer that with explained variance. Here, the explained variance ratio will tell us how much of the total variation in the original dataset is captured by each principal component. The first number corresponds to principal component 1, and the second number corresponds to principal component 2. And run this, and we see that we get 0.36 and 0.19. What does that mean? Here, that means the first component will capture around 36% of the variance, and the second component captures around 19%. Together, these components would capture around 55% of the total variance in the original dataset. We can calculate the total directly here. See, here our calculation here will show us that both of these components capture around 55%. When interpreting this number here, a higher value means the reduced version is preserving more of the original structure. A lower value here means more information was lost when we compressed the dataset. For visualization, two components are often useful because we can plot them easily. For modeling, however, two components may not always be enough. Sometimes we may want to keep more components so that we can reduce the number of features while still preserving most of the information. To understand how many components we might want to keep, we can fit PCA without forcing it down to only two components. When we create PCA here without specifying a number of components, scikit-learn will keep all the possible components. This lets us inspect how much variance is explained by each component and how much variance we preserve as we add more components. To actually visualize this, let's create a cumulative explained variance plot. This graph here is designed to help us think about PCA as a trade-off. We've set it up so the x-axis, we have the number of principal components, and on the y-axis, we have the cumulative explained variance. Cumulative here will mean that we're just adding the variance together as we include more components. The first point shows how much variance is explained by the first component alone. The second point shows how much is explained by the first two components together, and so on and so on and so on. This kind of plot is useful because we usually don't want to keep every component. If we kept all of them, we really would not be reducing the dimensionality of the dataset, and that's the whole point. At the same time, we don't want to keep too few components and throw away too much information. The cumulative variance plot will help us choose a reasonable middle ground. For example, you might look at this and say, oh, with 8 principal components, we can explain around 92% of the variance. At 6 here, you might say it explains 85% of the variance. Another cool feature here about scikit-learn is that it'll let us choose the number of components based on a variance threshold instead of manually choosing a specific number. For example, here we've set n components is equal to 0.95. This means we're asking PCA to keep enough components to preserve 95% of the variance. This is different from n components is equal to 2 from before, where we exactly asked for 2 components. Here, we can take a look at the shape now. The shape of this will tell us how many rows and columns we ended up after PCA. The number of rows stays the same, in this case 178, because we don't really lose any observations. What changed here is the number of columns, which is 10, whereas we had 13 before. The original features here are replaced by a smaller set of principal components. At this point, we've seen how to run PCA, how to plot the results, and how to check explain variance. But conceptually, it's also worth understanding what it's doing behind the scenes. PCA specifically creates new axes for the data. These axes are chosen based on the directions where the data varies the most. The first principal component points in the direction of maximum variance. The second principal component captures the next strongest direction while being separate from the first, and the remaining components continue the same idea. Because of this, principal components are usually combinations of the original features. For example, in the wine dataset, one original feature might be alcohol content and another might be color intensity. But principal component 1 could combine several measurements into one new direction. And that's why PCA can be so powerful, but it's also one reason it can be harder to interpret than the original features themselves. Here, we can inspect how the original features contribute to the components by looking at the loadings. The components attribute tells us how each original feature contributes to each principal component. In this table, each row is a principal component, and each column is one of the original features. The numbers here are often called loadings. A larger positive or negative value means that the feature has a stronger influence on that component. The sign here matters mathematically because it tells us the direction of the relationship. When you're first learning PCA, it's usually enough to notice which features have larger absolute values. This table here helps us understand what PCA is emphasizing, but we should still be careful. Principal components are not always easy to describe in plain English because they're built from combinations of features rather than just one clean original measurement. As you start using PCA on your own datasets, you'll usually use it in a few common situations. One common use case is visualization, especially when you have too many features to plot directly. Another is preprocessing, where PCA can reduce the number of input features before training a machine learning model. It can also be useful when many features are correlated, because PCA can combine overlapping information into fewer components. With that in mind, there are some trade-offs we should be aware of. PCA is a linear method, so it works best when the important structure in your data can be captured through linear directions. If the structure is more complex, methods like kernel PCA, TSNE, or UMAP may be more useful, especially for visualization. PCA is best understood as a tool for simplifying data and should not be treated as the magic solution for every dataset. It's designed to help you reduce complexity, visualize the structure, and make modeling more efficient, but it still requires sound judgment. It's up to you to decide how many components to keep, whether explained variance is acceptable, and whether the loss of interpretability is worth the benefit of reducing dimensionality. Once you're comfortable with the basic Python workflow, you can start experimenting with larger datasets, different numbers of components, and different ways of using PCA as part of a machine learning pipeline. Thank you guys for watching, and I'll see you guys in the next video.